Assalamualaikum and good day everyone. My name is Intan binti Syamuddin and today I will be presenting on nighttime scintillation detector. In this presentation, I will explain the basic working principle, radiation interaction mechanism, performance characteristic, application, case study and finally the limitation and advantage of nighttime detector. Radiation detection plays a very important role in many areas such as medical imaging, environmental monitoring, nuclear security, and scientific research. One commonly used radiation detector is the scintillation detector. The basic idea is simple. Radiation energy is converted into light and then this light is converted into a measurable electrical signal. Among many scintillators, sodium iodide activated with thallium or nightthallium is widely used because it offers a good balance between high detection efficiency, reasonable cost, and practically operation at room temperature. Now, let's look at how nightthallium works. When a gamma photon enters the nightthallium crystal, it interacts with the crystal material and excites electrons. As these electrons return to their ground state, they emit visible light, which we call scintillation light. The thallium dopant plays an important role here. It increases the light output and shifts the emission wavelength into the visible range, which is ideal for detection. This light is then detected by a photomultiplier tube or PMT, which converts it into an electrical pulse that can be processed and analyzed. So there are three main gamma interaction mechanisms in nightthallium. First, we have the photoelectric effect, which dominates at low gamma energy. In this process, the gamma ray deposits all its energy, producing a full energy peak. Second, we have the Compton scattering, which occurs at intermediate energy. Here, only part of the gamma energy is transferred, producing a continuous Compton background in the spectrum. Lastly, we have the pair production, which happens when gamma energy is above 1.022 MeV. This process creates an electron-positron pair. All these interactions produce scintillation light proportional to the energy deposit in the crystal. Next is the signal generation process. The scintillation light first strikes the photocathode of the PMT, releasing electrons through the photoelectric effect. These electrons are then multiplied through a series of diodes, producing millions of electrons from a single photon. Finally, the electron reach the anode, producing an electrical pulse. The pulse height is proportional to the gamma ray energy, which allows nightthallium detector to be used for gamma spectroscopy. Then we move to the energy resolution performance. Energy resolution refers to the detector ability to separate closely spaced energy peaks. For nightthallium, the typical energy resolution is about 6 to 8% FWHM at 662 keV using a CS137 source. While this is lower than HPGE detector, which have excellent resolution, nightthallium resolution is still sufficient for many practical applications, especially where high efficiency and portability are more important. Nightthallium detectors have high detection efficiency mainly because of their high density, the high atomic number of iodine, which is Z equal to 53. They are especially effective for detecting gamma rays in the range of about 100 keV to 1 MeV. This makes them very suitable for low activity sample and environmental radiation monitoring. Nightthallium detectors also known for their high sensitivity, meaning they can measure radiation level close to background. They have a fast decay time of around 230 nanoseconds, which reduces pulse pileup and allows high count rate measurement. Because of this, nightthallium detectors are ideal for real-time monitoring, such as in nuclear medicine, emergency response, and also the field survey. So there are some key application areas include. For the first one, we have the medical imaging that used in the case of SPECT gamma camera. Second, we have the environmental monitoring for air, soil, and water. The third one, we have the security application that use such as portal monitor and health survey meter. And lastly, we have the research and education, particularly in university laboratories for gamma spectroscopy. Now we move to the first case study by Saidi that focus on improving gamma spectroscopy. So by combining thallium detector data with K-nearest neighbor algorithm, the study achieved better separation of overlapping gamma peaks. So this show that with modern data processing, thallium detector can still provide enhanced performance while maintaining their cost and portability advantage. The second study by G that involved continuous environmental monitoring near nuclear facilities. A network of thallium detector was used with wireless data transmission and automated alert. The system successfully provides a real-time dose rate measurement and reliable operation under various weather conditions, making it suitable for long-term safety monitoring. And the third study by Naim that focused on measuring natural radionuclide in soil sample. By using thallium detector with proper lead shielding and calibration, accurate activity measurements were obtained. This demonstrates that thallium provides a practical and low-cost solution for large-scale environmental survey. Despite its advantage, thallium has several limitations. Firstly, it has moderate energy resolution, so it is not suitable for high-precision spectroscopy. The second one, the crystal is hygroscopic, meaning it absorbs moisture and must be hermetically sealed. It is also mechanically fragile and sensitive to shock. In addition, it requires a stable high voltage supply. It temperature sensitive and is mainly suitable for gamma radiation only. To summarize, I put beside the advantage and also the limitation. Advantage include about high gamma detection efficiency, fast response time, room temperature operation, portability, lower cost compared to HPGE detector. While for the limitation, it include for moderate energy resolution, fragile and hygroscopic crystal, high voltage requirement, and also the temperature sensitivity. In conclusion, thallium scintillation detector remain one of the most widely used radiation detectors today. Although they do not offer the highest energy resolution, their high efficiency, fast response, low cost, and ease of use make them extremely valuable in medical, environmental, security, and educational application. Overall, thallium detector continue to be a reliable and cost-effective solution for gamma radiation detection.